Welcome back. The last topic for this section is differential equations. When I say a differential equation, I'm referring to any equation where a derivative, so normally we're thinking about the function being y, so a derivative of y, may be a first derivative or second or higher order. Potentially, you might have in the equation also y itself showing up, and often you'll have the variable x showing up in the equation itself also. So something like d squared y dx squared plus y equals 0. That's a differential equation, and that's because it's an equation and there's a derivative inside that equation. So what, of course, we're always interested in with equations is solving them. And so when we're looking at a general solution to a differential equation, that's going to be some function y of x that when I substitute it into the original equation, the differential equation, it makes it a true statement. So if I were looking at solving this equation, I'm trying to find a function y where when I add it to its second derivative, I get 0. These general solutions usually involve one or more constants of integration. So when we say general solution, it's because it's actually an equation that contains a family of solutions. So if I'm looking at the equation that we started with, the d squared y dx squared plus y equals 0, if I wanted to show that this is the general solution, constant 1 times sine plus constant 2 times cosine, to show that, all I need to show is that if I take that function y and substitute it in, and also substitute in the second derivative of y, that the two things will add up to 0. So let's do that. Let's find our first and second derivatives. So first derivative, dy dx. So my function has constant c1 and c2 in front, and of course these are just constant multiples, so I don't need to worry about that for my derivatives. So c1 times sine, the derivative of sine is cosine. And then derivative of cosine is negative sine. So instead of plus c2 times sine, I would have minus c2 times sine. And if I were to take the second derivative, then the derivative of cosine is negative sine, so I'll have minus c1 sine and plus the derivative of sine is cosine, so I'll have a minus c2 cosine. And now I can confirm that this function y is the solution for the equation, because if I go to my equation and look at the left side, I have second derivative plus the original function. The second derivative, that's minus c1 sine x minus c2 cos x. The function y itself is c1 sine x, c2 cos x. And that indeed all adds up to 0. So left side is equal to the right side. So that means that any function in this form, so for example, y equals 3 sine x plus 9 cos x, that'll be a solution, as would any other combination of constants c1 and c2. All right, so we want to find a general solution to this differential equation. And I guess the first thing I'm going to do is I'm going to rewrite it so that I have dy dx on one side, and I'll move that secant squared to the other side. And I'm going to do more work for this one than I will for ones in the future. So once we sort of see the reason why things work out the way that they do, then we can sort of generalize and save ourselves a little bit of extra work. So I have my derivative written, dy dx equals 2 plus secant squared x. And now I'm looking at this equation and I'm saying, well, if the left and the right side are both equal to each other, then they should both have the same indefinite integral. So if I integrate the left side with respect to x, and if I integrate the right side with respect to x, they should both have the same left and right sides. So when I look at y prime, the derivative of y, if I integrate that, that should just be y. An antiderivative of y prime should be y. And of course, constant of integration, I'll have some constant c1 there. For the right side of my equation, I have 2 plus secant squared of x, and I'm integrating with respect to x. The integral of 2 is 2x. The integral of secant squared is tangent x. And of course, I've got a constant of integration there as well. So right now, it looks like I have two constants of integration, but of course, these are two constants that are being combined together. So if I were to just make a little note to myself and say, well, let's replace c2 minus c1 with a constant c, then I have the following. Y is 2x plus tangent x plus c as my solution. And if I wanted to, I could go back and check. So if I were to take the derivative of this, dy dx, substitute that in and subtract secant squared, hopefully it should be equal to 2, that it would satisfy the original equation. So in general, and here are the steps that we're going to be skipping going forward, I know that the plan is we're going to integrate both sides with respect to x, and I know that on the left side, it's going to be just the same as y itself. So really, when I do this for real the next time, it's going to be that I'll jump ahead to saying y on the left side, and then the right side will be that indefinite integral of 2 plus secant squared. I'm also going to keep in mind that, yes, even though technically there might be two constants of integration, I'll be able to combine them together to make just one. So again, that's a little bit of simplifying my life that I'm going to do for myself. So we'll use that here where we're going to find now not just a general solution, but a particular solution. So a general solution that had constants of integration, that was a collection of all the possible solutions you could have. But now if we have some sort of initial condition, for example, we know a particular y value for a particular x value for our equation y as a function of x, we can use that to figure out what our constant of integration c needs to be. So to find our particular solution, we first start off finding the general solution. And right now, I already have things in the right form. I've got my derivative on one side, and everybody on the other side is just in terms of x. So I know that if I wanted to find y, I would just need to integrate with respect to x, the right side. And that's not too hard to do because I know that the antiderivative or an antiderivative of sine is negative cosine. And for 4x, it would be 4x squared over 2, which is the same thing as 2x squared. And then, of course, plus our constant c, and that would be our general solution. Now, if I wanted to use my fact that I know that y of 0 equals 6, that means that I would have 6 is my y value when 0 is my x value. And I can go ahead and solve and find that c should be equal to 7. So that means now I can give my particular solution by writing in that constant 7. So it's the equation y equals minus cosine x plus 2x squared plus 7. It's part of that family that's the general solution, so it does solve the original equation, and it also satisfies that initial condition y of 0 equals 6. So that is why it's the particular solution to that problem. Okay, let's do another one. We want a function that passes through this point, 3, 4, and it has derivative f prime is equal to 3x squared minus 7. So if we're thinking about y as being our function f of x, then we know that if it has the derivative of 3x squared minus 7, then we know that y, or f of x, should be the integral, indefinite integral of 3x squared minus 7. And that's not too hard to do. So 3x squared would be 3x cubed divided by 3, which is x cubed, and then minus 7x, and of course plus our constant c. So that would be an equation for our function f of x, except we also need to know the constant c, and that's given to us by using the fact that our equation has to pass through the point 3, 4. So now let's use the fact we know that f of 3 is equal to 4, or in other words, the y value is 4 when x is 3. And we come up with a value of c as -2. So now I can write out my particular solution. My function f of x, the one that I was looking for, is x cubed minus 7x minus 2. That's a function whose derivative is 3x squared minus 7, and you can check that out very easily. Yep, it is. And you can also confirm that it passes through the point 3, 4. So now we're going to come back to position and velocity and acceleration, which we talked about back in chapter 3. And in fact, I gave us an equation for an object in free fall, and I said we'd come back and sort of explain where that equation came from. And it's this, the relationship between the three things. We know that if you have a position function and you take the derivative of it, you get the velocity function, because velocity is how is position changing over time. And if you took the velocity function and found its derivative, that gives you the acceleration function, because acceleration is how velocity is changing over time. So you can say to yourself, well, if you wanted to do antiderivatives and say, well, the indefinite integral of acceleration should be velocity. And if you did the indefinite integral of velocity, that should be position. And of course, if you wanted to do it from acceleration and find position, you could integrate once to find velocity and then integrate again to find position. That means there's going to be two different constants of integration that are going to show up. That's why for these sorts of problems, when I'm talking about objects in motion, I need to have at least 2 bits of initial information, initial speed, initial position, to help me figure out what these constants need to be. Okay, so we have a bunch of things going on here. A coin is initially tossed into the air from an initial height of 1.2 meters. So the position when time is 0 is 1.2. Positive because we're above the ground. We're moving with an initial upward velocity. So our velocity when we initially start, it's going upwards, so positive, 4.3 meters per second. If it was throwing things with a downward velocity, then the velocity would be negative. That's why for acceleration, why it's negative, because when you fall, you are accelerating towards the Earth. You're moving down, accelerating downward. On planet Earth, acceleration due to gravity is negative 9.8 meters per second squared. So I know that my acceleration function is easy. It's just a constant function. So if we wanted to know what our velocity function would be, that would be the indefinite integral of acceleration, or indefinite integral of negative 9.8 dt, which is negative 9.8 t plus our first mystery constant c. So the first thing that we can do here is take a little note that we could go right ahead and solve for what our constant C1 needs to be. And that's not too hard to do because we have one piece of information. The velocity when time is 0 is 4.3. So velocity of 0 is 4.3. If we put that into this function that we've now got, we can say, well, 4.3 should be negative 9.8 times 0 plus c1. Or in other words, our constant c1 is just our initial velocity of 4.3. So now we know what velocity is. Velocity is negative 9.8t plus 4.3. And if we wanted our position function, now we just need to do the same sort of thing. Position is the indefinite integral of velocity. And when I find the indefinite integral of that, negative 9. I got excited there. I already added powers and didn't quite get there yet. So now we're doing that. 9.8t to the 1. I add 1 to the power to get me 1 plus 1, which is 2. So t squared, and divide by the power. The negative 9.8, when I divide that by 2, that gives me negative 4.9. So I'll have negative 4.9 t squared plus my initial velocity times t plus another constant c. And I'm running out of room to fit this in here, but if we use that second little bit of information that s of 0 is 1.2, we'll have 1.2 is equal to 0 plus constant 2. So in other words, constant 2 is 1.2. And we'll have our position function now as negative 4.9 t squared plus 4.3 times t plus 1.2. Okay, so now we want to ask questions about things like what happens to this coin, when does it hit the ground? So we wanted to know for this, when it hits the ground, when is the position 0? And so now I just have to solve a little quadratic function. So negative 4.9 t squared plus 4.3 t plus 1.2 equal to 0. So I'm just going to use the quadratic formula. So negative 4.3 plus minus root of 4.3 squared minus 4, negative 4.9, and 1.2 all over 2 times negative 4.9. And when I run this through my calculator, I get two possible values, one of them being 1.10015 and the other one being about negative 0.2226. And of course, the negative one is one that we're going to have to reject because that is the coin hitting the ground before you throw it. That doesn't make any sense. So we're rejecting because in this scenario, time starts at 0. So I can say the coin hits the ground after approximately 1.1 seconds. Last part, we wanted to answer the question of when does the coin reach its maximum height and what is the maximum height? Of course, if we wanted to maximize position, then we would need to find where is the derivative of position equal to 0. That would be critical numbers. That would be where maxes and mins happen. And of course, where the derivative is equal to 0, that is where velocity is equal to 0. And we know what the velocity equation is. That's negative 9.8 t plus 4.3. And when I calculate that, I get about 4.4388 seconds. So after 0.4388 seconds, the coin reaches maximum height. You might be asking yourself, how do you know that it's a maximum and not a minimum? And my answer to that is courtesy of the second derivative test. We know the second derivative of position is the acceleration function, which is negative 9.8. In other words, we are always concave down. So if you have a critical number that happens because the derivative is equal to 0, if you are always concave down, then at that point you must have a maximum. So that's my justification as to why I know the coin is reaching its maximum height at that point. And then finally, the maximum height, to find what that is, I need to go and use my original position function and put in that 0.4388. And when I did, I got my position was about approximately 2.143. So the maximum height is approximately 2.143 meters.